capacitors, let's say something like, let's do something like this. So the capacitor with initial charge of 15 microcoulombs and capacitance of 2 microfarads is connected with an inductor of inductance 15 millihenries. Then we can ask some questions based on that. What is the period of the motion? What is the period of the oscillation? What is the charge of the capacitor at t is equal to, let's say 120 milliseconds? What is the current in the circuit at t is equal to 120 milliseconds? What is the energy of the capacitor at t equals to 120 milliseconds? And energy of the inductor at t is equal to 120 milliseconds. D, at what times within one period will the energy of the capacitor be 3 times the energy of the inductors? So something like that is a good oscillation type question. So basically they're giving energy to each other, back and forth, just like a spring and a block. And then the capacitance is 2 microfarads. That's how you get the omega. So 30 times 10 to the power 9 negative, that's square root, then reciprocate. Oh, that's pretty fast. So the frequency is very, very high, 5773.5 radians per second. And then the period is 2 pi over omega. So I'm going to reciprocate the omega times 2 times pi. Ooh, 1.088 milliseconds. So I'm going to go to the right, 1.088 milliseconds. So that's the period of the motion. So in other words, they're going to exchange charge to each other and energy every 1.088 milliseconds. It's oscillating very, very fast frequency. Very high frequency and very short period. Okay? So now at what is the Q of t at t equals to 120? So what's the equation for Q? A sine of omega t plus phi. Let's see here. What's the initial conditions in our case? Oh, the initial conditions is that the charge is C with initial of, the initial condition is that the charge is 50 microcoulombs and the initial current is 0, right? Because otherwise it would have also said that the inductor has some current in there. So the inductor has 15 millihenries, but there's no current in the inductor. So the current, the initial condition, current I of 0 is just 0. But Q of 0 is 50. Q of 0 is 50. So if it doesn't tell you that there's an initial current, then that means the initial condition is that it's 0. You see? So then you go over here to this equation, and then the other equation, the current equation, right? And then you apply the initial conditions. I of t is a omega cosine omega t plus phi. So then you put 0 for t, right? You put 0 and you get here the initial charge is 50 microcoulomb, a sine of, and then just phi. And then this is just 0, right? And then here the initial current is 0. A omega cosine of phi. Right? So what is a possible value of phi? Well, if you want 0, phi must be either pi over 2 or 3 pi over 2, right? Yeah, I think pi over 2 would work. Phi is pi over 2. That would make this guy 0. Cosine of pi over 2 would be 0. That would satisfy the initial condition of the current in the circuit. So that means the inductor has no energy in there at the beginning. No current and no energy. Okay, so then then we put this phi into here. So the purpose of the phi is pretty much to satisfy the initial conditions, and A is the amplitude of the oscillation. So combination together, they help meet the criteria of the initial condition, you see. So if you put phi here, you're just going to get 1, and then A is going to equal 50, right? So that means the equation for Q is 50 sine of, and then whatever omega is, 5773.5 t, and then phi is just pi over 2. And then there's a micro here. Okay, now I can answer this question. What is the Q at 120 milliseconds? So then I put here, okay? So I gotta be in radian mode. Put the radian and go 5773.5 times 120 milliseconds, right? Times 10 to the power. Okay, then plus pi over 2. Then take the sine of that times 50. Okay, negative 4.93 microcoulombs. That's the charge across the capacitor at that time, negative 4.93 microcoulombs. That would be the physics 101 equivalent of saying, what is the stretch amount of the spring at that time, right? So Q behaves like X. Okay, and then well, how about the current? But they want to know what is the current at 120. So then the current would be a W. So this one comes out 50 micro times 5773.5 times cosine of 5773.5 times 120 milliseconds plus pi over 2. So this section is going to have a lot more trig. You have to be in radian mode all the time. So now you have 5773.5 times. I'm just going to do 0.10.12 plus pi divided by 2 cosine times 5773.5 times 50, and that's a micro, so that would be 1, 2, 3, 4, 5, 6. Okay, so then that's negative 0.287 amps. So that kind of came out pretty big current. Right? Yeah, that's pretty high. Negative 0.287 amps. The negative just means that it's flowing this way, opposite to the direction of the direction of the charge of the capacitor at that instant. You see? Okay, so then once we have that, we could do UC/UL pretty easily. UC is going to be what? Well, once I know, let's see, half Q squared over C, I think that's the quickest way. I already know the charge of the capacitor, and then I could just do that. Yeah. 1/2 the charge of the capacitor. So 4.93 microcoulomb squared over 2 microfarads. That's it for the energy of the capacitor. So you just take the charge that we found, and then you square it. So 4.93 squared divided by 4. 6.076, and then micro squared over micro just gives you microjoules. So at that instant in time, the energy stored in the capacitor is 6.076 microjoule, right? And then the energy stored in the inductor is going to be 1/2 Li squared. So it's pretty straightforward for that one. You're just 1/2, and then this one is going to be the inductance. $15 millihenries, right? So that would be 0.015 Henry, and then whatever the current was, which was also large, 0.287 squared. So 0.5 times 0.015 times 0.287 squared equals, okay, if I want to write it as a micro, that'd be 607, 6, that's really large. 617.77 microjoules. So at that instant in time, the energy stored in the inductor is a lot larger than the energy stored in the capacitors. That would be the physics 1 equivalent of saying that the kinetic energy of the block, is a lot more than the energy of the spring. When would that happen? Near the natural equilibrium position of the block. The block would be going, let's say it's compressing, the block would be going very fast near the equilibrium position. So the kinetic energy is going to be very high, but the potential energy of the spring is going to be very low. So you see, at 120 milliseconds, the energy stored in the capacitor is very low, right? So that would be equivalent to the potential energy of the spring being very low near its equilibrium position. And then the kinetic energy of the inductor, right, is very high. That means we are at the natural equilibrium position of the inductor capacitor system. It's just harder to see it for an electrical system because there's no motion actually going on, you see. With a block and a spring, it's easier to actually see that. Okay, question D was, when is the energy of the capacitor 3 times the energy of the inductor within the first period of the motion? So within 1.088 milliseconds, how many times does this condition get satisfied? So how do we write that down? The energy of the capacitor is going to be half Q squared over C, right? So it's going to be 1/2. What's the equation for the Q? 50 sine of that thing squared over 2 microfarads. And this is also micro. So the general equation for the capacitor is that. And then the general equation for the inductor is half L. L is 15 millihenries. And then the I is going to be 15 micro times 5773. 5773.5 times cosine of that squared. So I'm writing the general equation down. So this is the energy of the capacitor. Energy of the capacitor. So then you have here 1/2, 50 squared. So 50 is going to squared is going to be 2500. Over, this is going to be a 2, and then sine squared of the thing in the parentheses, and there's going to be an extra microjoule. And then this one is going to be 1/2, 15, and then this is going to be 50 squared. So this was the current, so 2500 times 5773.5 squared times cosine squared. And then the milli times a micro squared. Right, so then this micro comes and cancels one of those micros. And then the 2500 cancels, that's good. and then the 2 cancels the 2. Let's see, so the micro cancels the micro squared. Then I have a milli times a micro. Okay, so then I have cosine squared can come down here and make this tangent squared. Tangent squared of that is equal to 2 can go to the top, 2 times 15, right? 2 times 15 times this thing squared, 5773.5 squared. Squared times a milli times a micro, which is a 10 to the minus 9. Okay, then I'm going to square root that.
That's a good question.
Yeah.
Did you count for the 3? You said you wanted to find.
Which one?
I'm not sure if I see it.
Which one?
Oh, the 3.
Oh no, I forgot. I forgot to impose the condition. Yeah. So then I have to put a 3 here. Yep, that's right. So you have to look at what the condition that the question is asking, and then impose that condition. So if it said when are they equal, then of course I would do that. If it's 3 times, then I have to put that. So then you have an extra 3 here. Okay, then I'm going to take the square root of this. So this can come out of the square root. So now I can write down what was in the parentheses, which was 5773.5t plus pi over 2. Then this one can come out, 5773.5. Then square root of 3 times 2 times 15 times 10 to the minus 9. Okay, now let's see that. Okay, so 6 times 15, 90 times 10 to the power 9 negative square root times 5773.5. Okay, so you have tangent of 5773.5 t plus pi over 2 is equal to 1.73205. But when I took the square root, I could have positive negative square root because it was tan squared, right? Tan squared is equal to this number. So then when I do that, I have to take positive negative. So it's like this. So if I want to find all possible values of t for which that condition is satisfied, I have to take the inverse tan of that. Okay, so inverse tan. Okay, so then I have to say 5773.5 t plus pi over 2 is equal to the inverse tangent of the positive value gave you that. And then that's in the first quadrant where the tangent is positive, or any pi multiple of that, plus n pi. Okay? And then you do the negative option, which is going to give you in the fourth quadrant. And then it's just going to give you negative of this, right? Negative 1.0471973349 plus n pi. Okay, so now you have to see how many of these give you answers within one period of the motion. And the period of the motion was what? 1.088 milliseconds. So how many answers are there within up to that period? So you could put here n is 0, generate the first answer, let's say, and then you just do this number minus pi over 2 this minus pi over 2 over that. Oh, but then that's going to give you a negative answer, right? If you try n is 0, it's going to give you a negative answer. So no, so you can't do n is 0. You have to at least start with n is 1. Here you have to start with n is 1. Yeah, that might work because the idea is that you want t to be positive. So let's try n is 1 here. So I'll have pi minus 1.04719 7349. Pi minus that, minus pi over 2. Yep, divided by 5773.5. So that's going to be 0.091 milliseconds. 0.091 milliseconds. Let me see, go 3 spaces. Yeah. Let's see here. That's one answer. Then I put n is 1 here, right? So this is going to give me the first. This is going to give me the second. Then I'm going to come back to here. So then this is going to be pi minus pi over 2, which is going to be pi minus pi over 2, which is pi over 2 plus that number. Pi divided by 2 plus 1.04719 7349 divided by 5773.5. That's the second time. 0.453 milliseconds. There's probably going to be 4 times where it repeats. That condition is met. So 0.453 milliseconds. Then I come back to here and put n is 2. Right? So 2 pi minus pi over 2 is going to be 3 pi over 2. Right? 2 pi minus pi over 2. Yeah. 3 pi over 2. So 1.5 pi. Then minus 1.04719 7349 divided by 5773.5. Okay, then the third time is going to be 0.635 milliseconds. Yeah, there should be 4 answers. So one more answer, and then it'll be close to that, the period. Then you go back to here and you put n is 2. And then 2 pi minus pi over 2 is 1.5 pi again. 1.5 pi. No. 1.5 times pi. Okay. Plus 1.04719 7349 divided by 5773.5. Haha. 0.998 milliseconds. Yup. Happy face. Some good trig there, huh? Ooh, with radians and checking the quadrants, you know, going all the possibilities within one period. Let's see. I think we answered all the questions there. T1, T2, T3, T4. Okay, let's finish with something like something a little similar to what we did for the RC circuits.